The amplitude of probability we have defined in quantum field theory is usually impossible to solve exactly because of the very complicated structure of the path integral. We will be able to solve it exactly only for simple cases like free field theory or using some approximations. The first one we are going to consider is the classical approximation. So we will take the classical limit for this amplitude. If I restore h bar in this expression, I see that for a classical system where the action is much greater than h bar, I can use a stationary phase approximation where phi c is a classical field leaving the action stationary. The action is a spacetime integral of the Lagrangian plus a source term. The differentiation acts on the field and also on the covariant derivative of the field. We will accept that the differentiation of the derivative is the same thing as taking the derivative of delta phi. We then integrate by part to make the derivative act on the left side. The last term appears because of the integration by part, and it only depends on the value of the field at the boundaries of space-time, which I choose to be 0. We already chose our field to be the vacuum at time goes to minus infinity and time goes to plus infinity. We now add the condition that at the edges of the universe, if that even exists, the field should be 0. This equation should be true for any variation of the field delta phi. Therefore, the only possibility is to have the term between the brackets equal to 0. That gives us the Euler-Lagrange equation for the scalar field. To get the classical field equation of motion, we need to substitute the Lagrangian density by its expression. The derivative with respect to phi is trivial. The other term involves only the kinetic energy, which we can rewrite as. So there are two covariant derivatives with a lower index to take into account. Note that I took care to use different dummy indices. The derivative terms are only non-zero when alpha is equal to mu. This is a Kronecker delta with Lorentz indices, so it is always 0 except when alpha is equal to mu, in which case it is equal to 1. We can now use the metric to raise the indices for the covariant derivatives. There is a sum over alpha and a sum over beta. However, only the terms where alpha is equal to mu and beta is equal to mu are going to survive. Putting all these terms together into the Euler-Lagrange equation, we get the equation of motion for classical fields.